Hello, I'm Hakyeong from KAIST. I'll present our work Dense Metric Depth Completion from Sparse Direct Time-of-Flight Sensors. Acquiring dense metric depths from a single image remains a fundamental challenge in computer vision. Despite recent advancement in monocular depth estimation, large-scale foundation models still suffer from scale ambiguity. To resolve this, we incorporate sparse depth data from a direct time-of-flight sensor. By pairing a standard RGB image with a dTOP sensor data, our approach delivers highly accurate dense metric depths that is ready for a wide range of downstream applications. Existing depth completion methods leverage foundation models through sensor prompts, alignment, or knowledge distillation. However, they face key limitations. PROM-DA and DMD3C are restricted to specific sensors, while prior DA is computationally expensive due to its two-stage pipeline. Finally, optimization and diffusion-based methods achieve zero-shot generalization but suffers from a low inference speeds due to multiple sequential passes. Our approach delivers zero-shot generalization for diverse dTOP depth data, including automotive LiDAR, lightweight consumer dTOP sensor, and sparse random points. Because our model is lightweight, it achieves the best balance of efficiency and accuracy. Prior methods depend on large foundation models for their performance, and they leverage sensor depths in a very limited way, restricting its use to decoder-level prompting or conditioning. Instead, we adopt VIT small with lightweight as a baseline for efficiency and devise effective depths and RGB feature fusion in encoder level using mask joint attention. Specifically, here's the overview of our method. Given high-resolution input image and a sparse depth, our model estimates dense image resolution metric depths and validity mask, indicating undefined depths such as infinite sky. Our main contribution is incorporating mask joint attention for RGBD feature fusion. We replaced two independent self-attention blocks with one joint attention layer to get better fusion results. Notably, since it keeps the original VIT structure, we can directly initialize both branches with pre-trained dyno version 2 weights. Unlike cross-attentions, joint attention concatenate the image and depth tokens to compute queries, keys, and values jointly, which makes the multimodal fusion highly efficient. Importantly, we use mask attention, which creates an asymmetric information flow. It allows depth to image attention, so the depth data can guide and perfectly refine the image features while preventing image features to harm geometric information from metric sensor depths. We initialize both RGB and depth branch with pre-trained dyno version 2 VIT encoder and train with regression end-to-end. To align with the statistical distribution, we apply log normalization using the minimum and maximum sensor depths, scaling values to minus and 1. These exact same normalization parameters are then used to denormalize the decoder output. Notably, because we don't constrain the network output to rigid 0 to 1 range, the model can still infer possible metric depths in the regions lacking reliable sensor data. To train the model, we devise dTOP depth simulation pipeline. We synthesize sparse dTOP depth maps from 16 large-scale synthetic RGBD datasets to overcome the scarcity of real data. Our pipeline models both flash and rotating dTOP sensor families by replicating their unique sampling distributions, sparsity patterns, and hardware-induced edge artifacts. We evaluate our methods under a zero-shot generalization settings using both real sensors and simulated benchmarks. We validated our methods across 6 benchmarks, including 3 real-world sensor datasets. On average, our approach achieves the lowest relative error while maintaining an inference speed on par with PROM-DA, the previous fastest method, but delivering significantly higher accuracy. Qualitatively, our method consistently recovers more accurate global geometry, particularly in the regions with extremely sparse or missing depths in lightweight detailed dataset. Our method also successfully recovers dense metric depths in autonomous driving LiDAR dataset. To wrap up, here are the key takeaways. First, our depth-guided dual-branch encoder enables highly effective RGBD and depth fusion. Second, it achieves strong zero-shot accuracy and efficiency in depth completion. Third, the model is trained solely on synthetic dataset thanks to our detailed sensor simulation pipeline. And finally, it delivers all of this with real-time efficiency. Thank you.